Thanks for drawing.
Yes, thank you. This is, after all, the only good chalkboard on campus, to my knowledge. I think it is. I mean, well, that one outside I've heard is good, but it's outside.
No, it's not.
It's not good. Okay, so we're in section 10.4, Dummett and Foote, and we're still looking at tensors. So I'm just going to try to hit some high points here. For example, he talks about definition. You have M a right R module, and L an abelian group. And N a left R module. Let's see here. R, I believe, at this point is a ring. I'm not sure if it's commutative even here. Well, anyway, R is a ring. I don't think it's commutative just yet. Then a map phi from the Cartesian product of M and N to the abelian group L is R balanced or middle linear. With respect to R. If phi of M1 plus M2 comma N is phi of M1 comma N plus phi of M2 comma N, and phi of M comma N1 plus N2 phi of M comma N1 plus phi of M comma N2. I regret not just saying this in words. And finally, phi of M, and here's where the middle linearity comes from. MRN is equal to phi of MR comma N. So you can move the R from one slot to another, all right?
But the R is not.
Yeah, R doesn't have to be commutative here, I don't believe. And then this gives us Theorem 10. So here's Theorem 10. Now we have ring with unity, all right? And M, L, M, and N as in the definition, okay? Then a map, oh wait a minute, I'm a dummy. Sorry. My eyes were jumping back up to the definition again. L, M, and N. Okay, okay. Nothing wrong so far. We'll let M tensor Rn be the tensor product of M and N, all right? And then let iota from M cross N to M tensor N be the R-balanced map defined as defined above. All right. All right, then number one, if phi from the tensor product of M and N to L is any group homomorphism then the composite map phi equal to big phi composed with iota is R-balanced. From M cross N to L, and 2, if we have, conversely, if L is an abelian group and we have, again, phi from M cross N to L, a R-balanced map, then there exists a unique group homomorphism big phi from M tensor N to L such that phi is equal to the composite of big phi with iota. So we have a picture. We have M cross N, M tensor N over R. So there's the iota map. And then we have the phi map like this to L, right? And we got the lowercase phi map like this. So you see how it works. Phi is equal to iota composed with big phi, like that. And the interesting thing here is this describes the following correspondence. So we on the one hand have R-balanced maps on M cross N, right, to L. Or you could look at group homomorphisms of the form like phi going from M tensor N to L. This is useful because like like a lot of times it's easier to check middle linearity, and then to use this theorem to get the group homomorphism on the tensor product as opposed to trying to do it directly. So like if you start looking how this theorem's used, a lot of times it's used, you check the that you have an R-balanced map, and then aha, by theorem 10 that, you know, induces a homomorphism over on the tensor product to the same thing. So wanted to mention that. It's kind of an important one. Next definition I need to share with you. If you have M is left our module over commutative ring R, all right, then the R comma R bimodule structure on M given by Rm equals to Mr. Okay, for all M in M and for all R in R will be called the quote-unquote standard R module structure on M. Okay. So many of our examples allow this. If we have like a left, if you have a left R module action, or if you have a right R module action, you can just define the other side by assuming that they commute like this and just letting that define the other sides. What I'm trying to say is if you have a left module action, you can induce a right module action and vice versa. They're really just a choice of notation. It's kind of like using columns versus using rows. All right. So I'm getting there. So we'll eventually get to the things I care about. It just they're all kind of like, they've got their tentacles up into the other parts of this chapter, which I don't want to get dragged into proofs of, you know. So again, R, a commutative ring with identity. M, N, and L, the left R modules. Commutative ring with identity, all right. And then the map phi M cross N to L is bilinear. All right. And I should really say R bilinear. If what? If you have phi of like R1 M1 plus R2, well, I don't need to do, I could just phi of R1 M1 plus M2, comma, N is R1 phi of M1 comma N plus phi of M2 comma N, and 2 phi of M comma R1 N1 plus N2 is phi, is R1 phi of m comma N1 plus phi of m comma N2. In other words, an R bilinear map is a map which is linear in the first and the second slots. All right. And then, so he says, Theorem 10 can be restated with this language as, so with this, in this context, Theorem 10, instead of having R-balanced maps, you get what? You have R bilinear maps, all right? So you just have R bilinear maps. If you have M and N, both with their so I guess the difference here is that now R is a commutative ring, right? I guess that's just pretty much the difference, right? So, and also we're assuming that you can factor the R out. Before we just assumed it could switch spots, right? Yeah, so corollary 12 adapts Theorem 10 to this more special context of a commutative ring with identity. Then we have all the examples we went over. And then, let's see here. He defines the tensor product of module homomorphisms, like let's see here. And I guess I can do that. So if you have M, let's say, suppose you have M mapped under phi to N, both R modules, right? And you have M prime mapped to N prime under, let's say, psi, right? Then you can, these are both R module homomorphisms, right? They preserve the R module structure. Then you can define phi tensor psi from M tensor M prime to N tensor N prime. These are all R tensors, all right? How do you do it? Well, basically, without dragging myself into the full statement of Theorem 13, all right? Theorem 13 has the complete statement of what I'm giving it as a definition, but it's actually stated as a Theorem 13, which proves the existence of this thing, right? So rather than doing the right thing, which is to present Theorem 13 and then say, aha, well, we define the tensor product to be this thing that we've constructed as shown in Theorem 13, you know? I'm just going to tell you how it works. So it works like this. So phi tensor psi acting on, let's say, little m tensor little m prime, what's it equal to? It's equal to phi of m tensor psi of m prime. And well, anyway, there's more we could say, but that's kind of the main thing. All right. And let's see here, what else can I tell you? If we have, the other interesting thing about the tensor product is if you have the tensor product of 3 modules, if you like M tensor N, and I'm hiding some details here, right? M tensor N tensor L, then this is isomorphic to M tensor N tensor L. Now what I mean here is you can take, see Audric, you can do this one first, then that one, or you can do these two first and then that one. But if we sort through all the proper theoretical details, as is expanded in great detail in Chapter 10 here of Dumb and Foot, you'll find that the tensor product is associative. That's one of its major features. The tensor product is an associative product. Okay, so, and that's true both at the level of spaces and elements. On the other hand, it is true, so that's corollary. So this is actually corollary 15. He has a similar thing before that. That's a statement about maps. But so that is corollary 15. Now here he's assuming R is commutative and the ML and N are all left R modules, all right? Then if you look ahead here, you see corollary 16. I just want to talk through it. Corollary 16 says, guess what? You can also talk about mappings from the Cartesian product of like K of these modules, right? You can have M1 through MK to L. And you can define an arc K-linear map being linear in each of the K slots, right? And there's an analog of Theorem 10 in that context as well, that you can look at the mappings. You can look at the K-linear maps on the Cartesian product of K modules, and there's a direct correspondence to group homomorphisms on the tensor product of the K modules to L. So that's corollary 16. And then there's also like very, very satisfying relations between, like Theorem 17, it's like, it just seems just, you know? So we've got this abstract way of multiplying spaces, right? And you've got this abstract way of adding spaces through we talked about the external direct product, right? Now we talked about the tensor product. So if you have M, plus N, right, tensored with, let's say, L, right? So what is that isomorphic to? It is, of course, it's M tensor L, right? Direct sum with N tensor L. So there's a distributive property for tensor products and direct products. And it goes on both sides too. It's not just, you can also do it like this, right? M tensor, say N plus L would be M tensor N plus M tensor L. All right. And then corollary 18 is important because it shows you one of the primary theoretical uses of the tensor. So corollary 18, here we have the free module N, which is just R to the N, all right? And, I mean, it's isomorphic to R to the N, right? I should say. So, if we look at extending the scalars basically this is the idea. You can extend scalars to S by tensoring with S. Now here I'm assuming that like R extends to S, and that's defined in a more technical sense in this section actually. The most naive way is when R is a subset of S, right? So like if R is a subset of S, there's a natural idea of extending it in that way. But he's a little bit more general than that in this section if you read it. Anyway, so not wanting to get into all that again, but the point here is that if we take S tensor Rn, all right, then that's isomorphic to Sn. In other words, if you tensor a free module over R of rank n with S, you get a free module of rank n over S. I know many examples of this, and this has so much application. Like, so really, in some sense, the first example that you probably see of the tensor product is complexification. So like, you know, if we have a real vector space, right, and we take the complex numbers and we tensor it with a real vector space, we get the complexification. Now the way that works, of course, is if I have, you know, alpha plus I beta, and I'm multiplying it by x plus iy, how does that work? I mean, it just works like you'd expect. It's alpha x minus beta y plus I times alpha y plus beta x. And so sometimes when I teach linear algebra, I define a complex vector space over a given real vector space by this rule, and then I show that that definition of scalar multiplication on linear combinations of x plus iy necessarily gives you the structure of a complex vector space. But truth be told, all I'm really doing is taking the tensor product of the real vector space with the complex numbers. And it's just that no one wants to write this like, I mean, technically you should write it like this, right? Alpha plus I beta, you know, tensor with, I guess, x plus iy. Well, I don't know. Let me not get into the weeds here, but so that would be one example. But there are others, right? Pick your favorite vector space over the reals, and if you take the tensor product with a complex number, what you do is just naively replace all of the real scalars with complex scalars. That actually could be understood as a tensor product with the complex numbers. So, and let's see here. Corollary 19, also just important in terms of just big picture kind of stuff. If you have the free module with S thing, S rank free module, tensored with the T rank free module, guess what you get?
S plus T.
Good guess, but actually S times T. And the reason for that essentially is that, so this has like basis EI, this has basis, let's say EJ, for 1 less than or equal to I less than or equal to J, M rather, excuse me, I'll get it eventually, S, 1 less than or equal to J less than or equal to T. And so when you tensor product the two things together, the basis for the tensor product of them I really shouldn't say basis here. I should say generating set. You know, it's free on this set. Let's say that EI tensor EJ. That's the basis. That's the set on which our tensor RS tensor RT is free. But here I and j both range from 1 to s and 1 to t respectively. So counting gives us s times t things. And then, so here's an interesting bit. Corollary 20, M tensor n is isomorphic to n tensor m. Right? And it's more than that. It's a little bit better than that. Proposition 20, I should say, not corollary. Proposition 20 tells us this. And it also tells us that, in fact, there's a unique R-module isomorphism from one to the other. Can you tell me what it is? What is psi of, where do you map little m tensor little n to?
Psi n. Yeah, psi n. Something psi n.
No, you're defining psi. You can't say psi something. You have to tell me what psi does.
Oh, it goes from n. It goes to n. It's like same thing, like n.
Same thing, but with n and m.
Yeah.
Yeah, exactly that. So indeed, that's the isomorphism. So, but this is a little bit counterintuitive in the sense that the spaces are isomorphic, right? But it is not true that m tensor n is equal to n tensor m. Okay, like the little ones. The element-wise, it's not true. But at the level of spaces and isomorphism, it's true. All right. So, I mean, m could be functions, n could be, you know, matrices of, these could be matrices of different sizes or something, right? And so like flipping the order at the level of elements, it's not equal, right? But anyway. And then finally, proposition 21 tells us that we can take the tensor product of R algebras and get a new R algebra. Do you remember what an R algebra was?
Right alinear map, or is it left?
So it's, you have a commutative ring. It's
So R, it's on the left.
it's a space which has R in the center of the algebra, right? The copy of R inside the algebra has to commute with everything. It was defined, oh, so long ago. Where was that thing? It's back on page 342. R, a commutative ring with identity, and R algebra is a ring A with an identity together with a ring homomorphism from R to A. All right, but we get past that. You just think of the algebra having R as a subset, although technically it just has a homomorphic copy of R in the subset, which behaves as the center of the algebra. But anyway, you can take the tensor product of R algebras and get a new R algebra. All right, so that's also sometimes nice. Like that's one of the things we could build new examples from in our research if we felt like it, yeah. All right, so those are the high points from the study of, you know, what's the word? Tensor products. I will say a little bit more about tensor products, but everything else I have to say, I want to say in the context of vector spaces, okay? So, well, that's not entirely true. In the section 11.4, 11.5, he introduces something called the tensor algebra. And so the tensor algebra is an algebra built from the tensor product that it's this big associative algebra that we can do lots of things with. Okay, so that brings us to, you want to take a break?
Yeah, I need coffee.
That's cool.
That'll be the last.
It's all right.